Thank you.
There you go. Yes.
We start in 2 minutes, please.
All right.
Okay.
You guys can hear me well?
Yes, I can hear you.
Nice.
Very well. Okay. To start the afternoon session, Professor Matheus Duzi will talk us about infinity categories. Professor Matheus graduated from the master's degree at the University of São Paulo, and his line of research is general topology, topological games, and selection principles. Please, Professor, you can start.
Thank you. Thank you. Thank you for the organizers. Thank you to the organizers for the invitation. I'm very happy to be presenting here. This is a joint work with Professor Paul Sheptytsky and Professor Walter Polen from York University, both from York University. And this is uh, about a joint work that I mainly did when I was in Toronto working with them. So I'm going to talk a little bit about categories, but I'm going to talk a lot about infinite games. And at the end, we're going to talk about topological games. We're going to sprinkle throughout the presentation. So that's where the topology comes in. Uh, so let's see. Okay. So I'm going to start by explaining what are these objects that I'm calling infinite games. I'm going to give some examples uh, and some properties, some basic definitions. Then we're going to talk about the morphisms because we're going to talk about a category. So we're going to talk about what are considered to be game morphisms. And finally, we're going to talk about these categories of games that we form with these morphisms and how we can see some topological games as functors. So, infinite games. Intuitively, we're going to talk about games which are um, between two players, Alice and Bob. These are the two players that we're going to consider here. They are turn-based, and Alice starts. The two players compete, so they are not gonna. Whenever the game finishes, we declare one of them has a winner, and only one of them. The other loses, so they're competing. We have no draw, so whenever a game wins, we definitely declare one as a winner, and the other has a loser. And the game's at perfect information. This is a game theory jargon, which basically means that this is not a game like a card game where you have hidden information on the game. You have your cards and you don't show your cards to the opponents. So you have things about the other player that you don't know about. So these games, everything about the game is known. Everything is on the table. Both players know everything about the game at the current moment. So this is perfect information. And they are going to be infinite. They will have only infinite countable runs. This is a restriction that is important when we're dealing with the category, but that's not all that important, because if a game has finite runs, we can always extend that run to an infinite one by making the players play some dummy variable and declare the winner of the original run. So this is not really a restriction. This is more of a technical restriction. But formally, what we mean by an infinite game is a pair TA, where T is a set of finite sequences over a set M, and A is a set of infinite sequences over the same set, and such that these conditions hold. And there's a lot of notation here. I'm going to explain each of these notation. So by this symbol right here, what we mean is if you have a finite sequence, x0 to xn minus 1. So we have n elements of the sequence in the sequence, and this is exactly the length of the sequence. So this counts how many elements we have in the sequence. Now this symbol right here is the truncation of the sequence. So if we have a sequence x0 to xn, and we have a k that is less or equal to n, this is a truncation to the kth element of the sequence. So from 0 to k minus 1. So this is the truncation of the sequence up to that point. So what the first condition here is saying is that if we have a sequence that is in the tree, which we will call a moment of the game, if we truncate this sequence, if we look at the past, then this is also a moment of the game. This is also a sequence that is in T. So this is what condition 1 means. So for every moment of the game, if you look at the past of that moment, the past is also in the game. Is also a moment of the game. And now in condition 2, we have this symbol right here, which basically means if you have a sequence, this just adds x to the end of the sequence. So you add x, the element x, at the end of the sequence T. This is what it does. So what this is saying is that whenever I have a moment, a finite sequence in the tree, I can always extend it somehow in such a way that it is still in T, still in T. And condition 3 basically says that this selected set A of infinite sequence is a subset of this collection of all runs of the tree.
Ya listo. Ya, entonces hay que avanzar hasta las 4 por lo menos, ¿ya?
Sorry? Was that with me or? Okay. So, sorry?
Continue, please.
Oh, okay. So the set A of infinite sequences is a subset of this set right here, which I define it as a collection of infinite sequences of M, such that their restriction always lie on T. So this will be the runs of the game. So A is a selection of runs of the game, G. So when we have only a tree, when we don't have a set A, we only have a T, which is a tree of finite sequences that satisfy conditions 1 and 2. We say that T is a decision tree over the set M. And all of our games will be infinite, so we will move. I will not be saying the word infinite every time. I will most of the time just say game from now on. And I spoke a little bit. So this is the intuition. This is why I called T a tree a few times. So every game starts with the empty sequence. And the idea here is that the sequences with only one elements are the choices that Alice can make in the game. So Alice will start the game and she will pick these elements which are in the tree T. This is the tree T of the game. And then Bob has these possibilities that he can choose, and he will choose one of them, and so on and so forth. And so the players alternate by choosing the sequences in the tree, one extending the sequence of the other, all while still remaining in the tree T. And then the idea is that they will play this for countably many times. They will play it infinitely many times, and then they will form an infinite sequence. Once they form an infinite sequence, that's the end of the game. And if this sequence is in A, then we will say that Alice wins the game. If this sequence is outside of A, then we say that Bob won the game. That's the idea. So to summarize the dictionary for a game TA, we say that a finite sequence in the tree is a moment of the game. That's something I already spoke a little bit about. An infinite sequence in this set that I defined previously is a run of the game. So it's that infinite sequence that the players build by playing the game. Okay. And this is a run of the game G, or a run of the decision tree T. If a moment of the game is such that it has even length, then we say that it is Alice's turn. So in the beginning, the length of the empty sequence is 0 because it has no element in it. So it is Alice's turn, so she starts. So once she makes her move, we will have a sequence which has a single element. So a sequence with a single element has length 1, which is odd. Then we say that is Bob's turn, and so on and so forth. So they keep alternating between each other. And we say that Alice wins a run of the game if that run is in the selected set. Otherwise, we say that Bob wins the run. So that's the gist of it. Let's start with an example, a concrete example. So suppose we have a non-empty topological space X, and we're going to define the following game. In the first inning, Alice will choose a non-empty open set U0 of the space. Then Bob will respond with a non-empty open set contained that Bob previously chose. And then Bob will respond with a non-empty open set contained in the open set that Alice previously chose. So they will alternate by choosing a non-empty open set contained in the previous one. They will build together a chain of open sets which is contained in one another. And then we will say that we will declare Bob as the winner of a run of this game if the intersection of all of his moves is non-empty. And then we will say that Alice wins otherwise. So this might feel strange, considering that I'm not talking about any tree here. I'm not talking about any set A. But the idea here is that with these rules, we can easily define the set T and the set A for this particular game. In this case, the set T will be the sequences of chains of the finite sequences of chains of open sets, non-empty open sets. And the set A will be the set of infinite sequences of chains of open sets, non-empty open sets, which has empty intersection. This will be the set A for this game. So that's the idea. Based on these rules, that's how we define the games in terms of the definition that I gave before. This is how you usually find games defined in the literature. I'm just telling you that with this sort of definition, we can obtain we can construct what I described in my definition, my more general definition of an infinite game. Of course, we have what I call the world's most boring game, which is the empty game. By vacuity, when I take M as the empty set, this will satisfy all the conditions for it to be a game. So the tree has no sequence, there is no payoffs, there is no set A. This is the game that is not played. This is the empty game. And this might feel strange, but this will be the initial object in our category, which makes sense because the empty set is the initial object in the category of sets, and in many other categories. Okay, so we can't talk about games without talking about strategies. This is probably the most important concept when we're talking about infinite games. So for a game G, we say that a non-empty subtree of T is a strategy for Alice in the game G if gamma itself is a decision tree. So we satisfy conditions 1 and 2 of the definition that I gave before. For every moment of gamma, if this is Alice's turn, then there is a unique element such that this is in gamma. This should be gamma, sorry. So what this is saying is that this is supposed to denote, to decode a strategy for Alice. So gamma is supposed to say exactly what Alice should do in the game. This is why there is a unique. So gamma is telling you, in this moment that is Alice's turn, Alice should do this, should choose X. This is what condition B is saying. And condition C is saying, well, if otherwise this is a moment that is Bob's turn, then this will hold, this will be also a moment of gamma for every X, which is a moment of the game before. So what this is saying is this is supposed to be a strategy for Alice. So this is supposed to tell Alice what she has to do in every possible scenario that Bob gives her. So this is saying that for every X that Bob could play in the original game, this will also have to be in gamma, so that gamma can tell Alice what she has to play in this moment. Furthermore, we say that gamma is a winning strategy if every run that is played according to gamma is going to be won by Alice. This is what is being said here. And of course, we can say the same thing. We can define what is a strategy for Bob, and it's basically the same thing as in flipping Alice for Bob in the definition. So it's pretty much the same. Okay. So why do we study games, infinite games at all? The motivation for this is we frequently find properties in studying mathematics, which are of the kind, it is possible to construct a sequence, an infinite sequence, such that this sequence has a given property P, for instance. Then the concept of games and strategies are used to define stronger properties than the one that is described above, which is something in the lines of, it is possible to construct a sequence which has a property, even with someone trying to hinder the process while you are constructing the sequence. So this is like, it is possible to construct, imagine you are Alice, so you're trying to construct a sequence, but then there's Bob making his moves along the way, which is trying to stop you from constructing the sequence with the property P. So this is the idea. So it's something that is stronger. So above, it is possible to construct somehow the sequence, and below it's possible to construct the sequence, even with someone along the way trying to stop you. So that's the idea. And to motivate, we have this classical theorem from Oxoby from 1957, which says that a topological space X is bare if and only if Alice has no winning strategy in the Banach-Mazur game, which I had just described this should be over X. Okay, so let's move on to game morphisms now. An amorphism between the games G1 and G2 will be a mapping between the decision trees of these games. And this mapping will have to satisfy a few conditions. So first condition is that for every moment of the first game, when you apply the mapping to this moment, this will have the same length than the moment you started with. So F preserves the length of the moment. This is the first condition. The second condition is for any moment of the first game, in every k which is smaller or equal than the length of the moment, if I apply f after truncating the moment, after truncating the sequence, this is the same as applying f and then truncating this. So this is like, remember, looking at the game, so when you have a moment of the game, a moment is a sequence. When you truncate the moment, this is like looking at the past. This is like looking at a moment in the past of that moment in the game. So what this is saying is that f is chronological in some sense. That is that when you look at the past and then apply f, that is the same as applying f and then looking at the past. So f commutes with looking at the past. This is the idea here. And then what makes it an amorphism, is that for every run which is won by Alice, this is what is being said here, for every run that Alice wins, if I look at the image by f of that run, which is written here, then this is also a run which is won by Alice in the second game. So f maps a run won by Alice into a run which is also won by Alice. So this is an amorphism. Of course, this definition prioritizes Alice. We're just talking about Alice in condition C. So we could define a bimorphism, which is the same, except that instead of asking that f maps a run won by Alice into a run won by Alice, we ask that f takes a run which is won by Bob, which is what is being said here, and maps it into a run which is also won by Bob in the second game. Okay. And to further motivate all of this approach, we have, let us recall this theorem from group theory, which is the theorem from Cayley, which says that for every group, there is a set such that G is isomorphic to a subgroup of the symmetric group of X of G. So again, this is a classical theorem from group theory. And we have something similar here, which is something on the lines that for every game, we have a metrizable space K of G, such that G is isomorphic to a subgame of the Banach-Mazur game over K of G. So in here, we have, in place of a group, we have a game. In place of a set, we have a metrizable space. And in place of the subgroup of the symmetric group, we have a subgame of the Banach-Mazur game. So it's a completely analogous theorem. And in here, there might be some confusion with, I use the term subgame here, which I haven't defined yet, but I define it right here. So it's what you expect. We say that a game G prime is a subgame of the game G if the decision tree of G prime is contained in the decision tree of G, and the set of all runs won by Alice in G prime is the set of all runs from G prime which is won by Alice in the game G. So this is basically saying that G prime is contained in G, and G prime agrees with G where Alice and Bob wins, agrees completely. So this is a subgame. Again, what you expect. Okay, so let's talk about these categories more in detail. So games A is the category in which objects are game and morphisms are amorphisms. Games B is the same, except you switch amorphisms for bimorphisms. Because when you look at the definition of an amorphism, if you compose an amorphism with another amorphism, it is again, the composition is again an amorphism. And the same thing goes for bimorphisms, but when you compose an amorphism with a bimorphism, things get messed up. So we separate the two categories like this. And of course, these two categories are absolutely isomorphic. And the way you compute this isomorphism is basically you take the complement of the selected set of runs, That's basically how you compute this isomorphism. This is a very trivial proposition. But we also have a few non-trivial properties of these categories, which is that they are complete and co-complete. So you can take products in these categories. And the products are the multi-board games, in fact. And you can also take co-products, which will be something like disjoint union of games. You can take equalizers, co-equalizers. You can take any limit, any co-limit in these categories. So you can build a lot of games out of other games in these categories. And moreover, this is for those of you who know what this means. C is also Cartesian closed. So you can take also exponentiation of games. You can take g to the power of another g prime, for instance. This makes sense and is very well behaved in the same way as when you take a to the power of b in sets. So among some other nice properties, such as being co-regular and having orthogonal factorization systems and other properties, for those of you who know of category theory. All right. Not only that, I'm not going to be able to talk about much of this. I just put this picture because I think it is quite a beautiful picture, and it gives a nice idea of where we are with these categories. So what this is basically saying is that, well, games B and games A are isomorphic, that we already know, but this is isomorphic to a category which is built on top of complete ultrametric spaces. It is also equivalent to a category which is built in the category of trees as in graph theory, and is also equivalent to a category which is built on top of a category of functors. And there's a bunch of adjunctions and reflective inclusions, co-reflective inclusions, topological functors here. It's a very nice picture. Now let us go to the main event of the presentation, which is how we look at topological games now as functors. So let us start by giving you an example of a topological game. So, but obviously the Banach-Mazur game is an example of a topological game. But also we have this game, which is a tightness game, which is called a tightness game in the literature, in such that for a topological space X in the fixed point of the space, we consider the following game. In each inning of the game, Alice will choose a subset of the space such that the fixed point is in the closure of that subset. Then Bob will respond by selecting a point of the set that Alice chose. And they will continue like this, so on and so forth. And we say that Bob wins the run if the fixed point is in the closure of every tail of the choices of Bob. So this is what's saying. If you look at the set of all the choices that Bob made along the run, X will be in the closure of it, in particular. And Alice will win otherwise. Okay, so this is the first example. And this can be seen as a covariant functor. How do we see it? Well, for each, this is the category of spaces with fixed points. So given a space with a fixed point, we play the game that I have just described to you with that fixed point. Nothing much special. This is what the functor should do with objects. Now on morphisms, something interesting happens in that in this category, the morphisms are continuous functions which map fixed point into fixed point. And then we can define the functor on this continuous function in such a way that, well, when Alice chooses a subset of X, You can just apply f to that subset, and then you can show that the fixed point of y is in the closure here. In fact, consider an open set containing this fixed point. Well, because f is continuous, the pre-image is open here. And because f of x is equal to y, this is an open set here which contains x. But A0 contains x in the closure, in its closure. So A0 intercepts this open set here. And that means that f of A0 will necessarily intercept the open set that we started here. And you can, in this way, show that this is, in fact, a bimorphism. This thing here that we're defining is going to be a bimorphism. So we have a functor. We have effectively a functor from the category of spaces with fixed points into our categories of games with bimorphism. And alternatively, let's look at another example, another important example for what we're going to discuss later. Given a topological space X, consider the game in which in each inning of the game, Alice is going to choose an omega cover. And what is an omega cover? An omega cover of the space X is going to be an open cover of the space, first of all, such that for any finite subset of the space, there is going to be one open set of the cover which contains the finite set entirely. So for every finite set of the space, there is an open set of the cover which contains it. This is an omega cover. And then Bob will respond by choosing one open set of the open cover that Alice just chose. And we will say that Bob wins the run if, when you look at all the open sets that Bob chose, and you look at the tail of this collection, this in and of itself is going to be an omega cover. It's going to satisfy the same condition above. And if it doesn't, Alice wins otherwise. Alice will win. Okay. So again, we can see this has a functor. Now we see this has a functor that goes from the category of topological spaces into the category of games with bimorphisms. How so? Well, for every space on objects, for each space, you play the game over that space. You play the game that I have just defined for you over that space. And on morphisms, again, something interesting happens, which is given a continuous function, these are the morphisms in the category top. We're gonna let cover f going from cover y to cover x. So this is a contravariant functor. It inverts the direction of f, right? And what do you do? Well, given an omega cover, you can take the pre-image by f of all the open sets here, and you're gonna get a collection here. You can show again that this will be, in fact, also an omega cover, given the fact that f is continuous. Well, the fact that f is continuous means that this will be a collection of open sets. But then you can show that if this is an omega cover, this will also be an omega cover, and so on and so forth. And in this way, you can show that this, in the way that it is defined, is going to be a bimorphism. And this is a contravariant functor, and it's clear because why we need to take a contravariant functor, because we need to take the pre-image of f in here. So that's why it inverts the direction. But okay, why is any of this relevant, other than perhaps being fun to look at topological games in another light? Well, let us remember, or let us get to know a classical theorem from Skippers, which says that if we start with the T3.5 space, meaning that every point right, that every point and closed set is separated by a continuous function in the real line, then Alice will win will have a winning strategy. This is what the notation means. Alice will have a winning strategy over in the covering game over this space, in the covering game over X, if and only if Alice has a winning strategy in the tightness game over the space of continuous functions of X, when the continuous function that is selected, the point that is selected in this space, is the constant 0 function in here. And the same thing is true for Bob. So this is a well-known result in selective games, in the field of selective games. And it would be nice if we could find, well, we have two functors. For each of these games, we have a functor. And we know that two functors might relate to one another through natural transformations. So it would be nice if we could find natural transformations which give rise to these results right here, which transport winning strategies from one game to the other and vice versa. That would be nice. However, we have a few problems. The first problem is that the functor of the Titanus game has top star has its domain. Its domain is the category of topological spaces with fixed points, while the domain of the covering game is just topological spaces. There is no fixed point here. So the domains of the two functors are different. And so there can't be a natural transformation between them. Furthermore, to add insult to injury, is the fact that one functor is covariant. It preserves the direction of the arrow. Remember this, in this functor, we take the image by f of the selected of the sets. And in here we take the pre-image. So this is a covariant functor, but this is contravariant. So this is another reason why there can't be a natural transformation between the two. But let us consider an intermediate functor, which is the functor of functions, which for each space, it selects the space of CP of X, the space of continuous functions of X, and selects the constant 0 function. Then on morphism, if F is a continuous mapping from one space to another, then CP of F inverts the arrow in the sense that you just compose with F. You take phi 2 and you compose with phi 2 with F. So you would have a continuous function, a function in CP of x2. And how do you obtain a function in CP of x1? You just compose it with F, and then you get a function from x1 to the real line. And that's how you do it. And of course, this will take the constant 0 function into the constant 0 function here as well. So this is a classical way to consider producing spaces of functions in a functorial manner. This is the same thing that it is usually done in vector spaces when you take the dual space. Now, we should note that the functors that we actually want to compare is the cover functor of the covering game. And it's not cover with tight, but cover with tight composed with CP. Because remember, the theorem says that Alice wins the game over X if and only if Alice wins the game over CP of X. So you want to first take CP of X, select the 0 function, and then play the game. That's this composition right here. So these are the two functors that we want to compare. And in fact, the issues we had, for instance, the domain of one was top with fixed points while the other was top. Now it is solved because this composition has domain top. So they have the same domain now. And while one was covariant and the other was contravariant, well, when this was covariant composed with something that is contravariant, now we have something that is also contravariant. So the two functors are now contravariant, and we can compare them in principle. And indeed, what we obtain is that there are two nice transformations from this functor to this functor that together entails Kipper's result. And what we mean by nice transformations here, I should point out, is some transformations that for each space, it's somehow its image. If we take a winning strategy for one of the game in here, and we take the image by the nice transformation, then we will have a winning strategy here as well, and vice versa. And if we take a winning strategy here, if we take the pre-image by the nice transformation, then we will also have a winning strategy in the other game. So we have this nice algebraic structure that is preserved, that sees this theorem has been preserved. That'll be all. These are the references that we used. Like I said, this is a joint work with Paul Sheptytsky and Walter Tolan. It is currently a work in progress, although we are very much in the final stages, and very soon we'll have a preprint available on archive. Gracias.
Thank you very much. Is there a question for Professor Matheus? We have a few minutes for questions. No? Okay. Again, thank you very much, Professor.
Thank you.
Okay. At this time, we present the participation certificate of Professor Matheus. Thank you very much for your participation in this third International Congress on Topology and related topics. Thank you again.
My pleasure. Could you send me this by email, please?
Yes, by email.
Okay, thank you.
Continuamos en 20 minutos, 18 minutos más o menos. Espero puedan continuar por acá. Vamos a...